Hello everybody, welcome to this recording of my keynote at the Field Programmable Logic and Applications FPL conference in Belfast. That was last week. I want to thank John McAllister for inviting me to Belfast. It was a great time. It was actually a wonderful social event in Crumlin Road jail, and it was quite interesting because I was just running this painting of a group of researchers in Crumlin Road jail through a network called Stable Diffusion, and it took me as a human more than 15 minutes to figure out that jail actually means jail in English, which is prison, and it felt like a prison, but it wasn't quite clear to me from the very beginning. But if you look at the automatically generated drawing, it's actually quite nice that the artificial intelligence already beat me, at least, in recognizing what this means, because these pretty sad walls were immediately presented. Also, it generated a red-haired researcher, so it obviously knew that I was there last week. Okay, so jokes aside, I'm glad to be able to present this keynote. Actually, I'm presenting this based on several requests I got after the conference that people had to miss it. They wanted to see the slides and ideally get a recording. So let me just record it here for everybody. It's going to be quite similar to a talk that I've given earlier at an online event, the XACC conference by Xilinx. There are some new things in it and some different perspectives. So it's maybe worth watching it. And if you've seen the XACC presentation, then I would recommend to just fast forward to the temporal vectorization topic, and I will make sure that it's annotated in the YouTube video, and watch that, and then you will see the most important update from this talk. Okay, so now let me start. First, I want to talk a little bit about the changing hardware constraints and the physics of computing. Like I open many of my talks trying to look at what is the past and how to go into the future. And here this diagram, many of you have probably seen. The last 40 years of computing industry were quite stable, albeit quite massively, exponentially growing over the first 30 years, until about 2005, 2006, when Dennard scaling stopped working. Dennard scaling really means that with the shrinking feature size, also the power consumption of the devices shrunk, which means we could actually proportionally increase the frequency, which you can see is true about from 1975 to 2005, 2006. And then the frequency could not be scaled anymore, yet the number of transistors was still scaled because Moore's law was still happily alive. And that led to the so-called multi-core crisis that Intel was touting, with a strictly or strongly increasing number of cores over time. So this led to the parallel programming, parallel computing revolution. And eventually, Moore's law will also die, and we will move forward to the next, I would call this the spatial computing, spatial revolution. And FPGAs are a perfect way to spearhead this direction and to understand better how to face these new requirements going towards the next generation of post-Moore computing, essentially. So, but looking to the past, we had basically running this race of shrinking, 30, 90 nanometers, smaller and smaller processes. The 45 nanometer process is notable for me myself, because as a young student, I started in the AMD factory in Dresden to simulate high-K dielectrica that have been used in order to achieve this process, 45 nanometer process, at the time when AMD still was operating their own foundries in Dresden. Now this is taken over by Global Foundries. But coincidentally, for that process, we also have pretty precise data presented by Mark Horowitz that tells us the cost in terms of energy for computing a floating point addition and multiplication and loading the two operands from various size memories. You can already see that it's nearly an order of magnitude more expensive to load the operands from level 1 cache, an 8 kilobyte cache in this case, 8 kilobyte SRAM, to then computing these elements. Furthermore, if you go to a larger cache, like a 1 megabyte, for example, L2 cache, it's another order of magnitude more expensive. And if you go to DRAM, it's a third order of magnitude more expensive. So you can already see locality plays a huge role. But then as we shrink, the question is, does it get better or worse? Today, Samsung and TSMC have announced 3 nanometer processes going forward. Many other companies are going to smaller processes, or at least having smaller processes like 1 nanometer on their roadmap in a research setting, maybe not ready for deployment, definitely not ready for deployment yet, but maybe ready for some lab deployment. And the question is, where do we stop, or what are the fundamental limits of this scaling? So one fundamental limit could be the Landauer limit, which is the fundamental energy required to either produce to flip a bit, essentially, from 0 to 1 or from 1 to 0. And this is about 0.2 times 10 to the minus 6 picojoules, extremely small, of course. And fortunately, we are more than 1,000,000x away from that today. So that is not a big scaling limiter, even in the far future. But another scaling limiter may actually be electrical data movement, where the loss is proportional to the resistancy of the wire times the length, which are basically two constants. Like the resistancy is based on the material, the length is the size of a chip, which hasn't been growing that much, divided by the cross-section area. And now, of course, what we are doing is we are reducing the cross-section area as we are reducing the size of these devices. And unfortunately now, the electrical loss in data movement is actually growing. So that is, of course, a problem. So we need to worry about locality, locality, locality. And we have three forms of locality. And the first two forms, spatial and temporal locality, are pretty obvious to you. I'm teaching them the second semester, so many of you who are watching this video know exactly what these localities are. It also, if you don't know, then please look it up on Wikipedia. It's relatively simple. But I want to introduce a third form of localities, what I would call control locality, that has not been called out like this in the past, but I would like to establish this notion a little bit more formally. For the first two forms, you can also read this overview written by a good friend, Didem, Trends in Data Locality Abstractions for HPC Systems. That's a very good summary. But now let me talk a little bit more about control locality. So how does control work in load store architectures? Well, first we have some form of memory with the operands in there. We have some form of arithmetic logical unit. We have registers. We have a control unit. We have a cache, and we have a data and control path, or a set of data and control paths connecting all of these units. So this is how von Neumann architectures look like. How do they now work? Well, we are loading an instruction from memory. This instruction executes, and then in this case loads an operand from memory. Then we load another instruction from memory. It loads another operand. So this is a so-called tick-tock architecture. The tick loads the instruction. The tock executes the instruction, which may be another load. You can see for every instruction executed, you load another instruction from memory. And then it executes the instruction and may or may not access memory in this. So this is an extremely high overhead way of doing things. In fact, if you're going back to Mark Horowitz's analysis in ISSC 2014, we actually see that more than 95% of the energy, the total energy, are produced by this control or consumed by this control overhead. And only 5%, like you see the little red thing at the end, is the actual addition logic. Everything else is overhead, essentially. So 70 picojoule per instruction on average. And we can actually go back to the 1970s, where Backus was already saying, why are we doing it this way? Why wouldn't we get rid of this von Neumann bottleneck and build architectures, or in this case, programming languages, but architectures are very, very similar. Fundamentally, an architecture is just a mapped version of a programming language onto a spatial hardware device. And why do we not do this mapping more directly? And there is a way to do it more directly. So here in this case, we could again have our memory with our operands. We could now distribute our ALUs. And these are now not arithmetic logical units in the common sense that they're programmable, but they're specialized units. Here's a plus, another plus, and a multiplication. Then we could attach registers, input registers and output registers right to these units, and we could have a specialized data path for these units. So you already see there's no real control path. The control is basically the synchronization between neighboring units. When something comes out here, that enables this next one, and when this times has both inputs, it enables the next one. So a little bit like a Petri network. So in this case, the data is literally flowing through this circuit, and there is very, very little overhead, because each instruction is now, there are no instructions. So it's essentially hard-coded into the structure of the system, and the load is also from very small memory. So it's 1 to 3 picojoule per operation in this case. So it's nearly 30, or more than 30 times faster in the best case than the, less energy consumption, not faster, than the von Neumann architecture. And this is what I mean by control locality. On the left side, the control is explicitly loaded through this control structure from main memory, very little locality because we have the whole control flow is consuming a lot of overhead. On the right side, we have extremely high control locality because the control is encoded into the structure itself. So now you could argue that, well, SIMD or SIMT units, vector CPUs, GPUs, have a higher control locality, which is very true because you only load a single operation to operate an array of units, an array of ALUs in this case. Yes, it definitely has better control locality. However, it still has the issue, and this is now the part of the control locality, which is not just control overhead, that you have to load all of the operands from a relatively large random access SRAM. And this is the Achilles heel of SIMT and SIMD architectures, while here, in this extreme control locality, the registers themselves are attached to the units and the data path is just custom made. So here we still have an all-to-all data path in the GPU or CPU, vectorized CPU case. So it is higher control locality, but still lower because you need to access those registers. And if you access a 1 megabyte cache essentially, or 1 megabyte SRAM, it is a 1 megabyte register file for that reason. It's 100 picojoule, while just loading 32-bit from a neighboring registers is 1000x less costly in terms of energy. So really high performance computing as we know it today is a data management challenge which requires spatial programming and thinking. And as an audience for the FPL conference, we understand this very well. And this is, I'm preaching to the choir. And you have been talking about this the last couple of days that I've been watching here. Really, HLS and spatial locality was all over the place. So this was just essentially a summary of the vibe in the FPGA community that I'm observing today. So data movement dominates everything. So now we summarize the vibe in the HPC community. So data movement is most important. There were many talks by the DOE, John Shelf and friends, and also Bill Daly that was pointing this already out in many different contexts. In fact, our own paper that we published at the MLSys conference in 2021 was pointing the same fact out for machine learning workloads. So in this case, transformers. So data movement is all you need. A pun on the attention is all you need paper that is really showing how to optimize with a purely data-centric view on data movement, optimize transformers more than 8% over a hand-tuned implementation. So that was our first paper in the MLSys conference, one of the first papers in the machine learning field from my group, and we immediately got an outstanding paper award at the conference because we hit the nerve with this. Like, everybody understands this, we just need to figure out how to really do it. Then in a slightly older paper by Shikhar Borkar and Andrew Chien, very influential, highly cited paper, The Future of Microprocessors, the word data movement appears 18 times on the 11 pages of the paper. And then comes this key sentence, data movement depends, the future of our computing essentially depends on sophisticated software to place computation and data so as to minimize data movement. So what does this mean? Well, what is this sophisticated software? How do we program today? Well, to a first approximation, we program today how we programmed yesterday. Well, or last year, or 4 decades ago, going back to the complaint of Bacchus. We do control-centric programming today. We worry about operation counts. We worry about flops as the metric in high-performance computing. We worry about operations when we count things in our classes. So, for example, when we count a sorting algorithm, we worry about the number of comparisons we do, not the data moved due to the sorting algorithm. The data movement is at best implicit because we count operations and then data movement just happens to fulfill the operational requirements and is very often invisible or ignored. It's a huge problem. In fact, thinking about algorithms as a human way, how I do things, I think in steps and not where I do these steps or how I connect these steps. So it's very deep, at least in my thinking, because I probably grew up like this and we may be able to change this, but at least I'm claiming that in many of our cultures, we think procedurally and not spatially. So this is somewhat of a problem. Do this, then that. So how do we now cross this chasm between algorithms and data-centric computing? So the algorithms we design are, of course, procedurally because that's how we think, but data-centric computing is spatially because that's how it executes on the chip. So we need to do something about this. So as I mentioned, domain scientists and algorithms developers are in a control-centric world, and they should remain there because it's how they think. However, performance engineers must be in the spatial data-centric world. And so what we propose is an intermediate representation to connect the two. So both may need to adopt a little bit, but we leave the domain scientist in control-centric and we leave or move the optimizer the performance engineer into data-centric. So there's actually a long rant that you can find on YouTube that I gave at a panel at Supercomputing 2001. It's actually not too long, it's like a 10-minute rant where I really make this point, and if you're interested in this, I recommend you look this up, and you can find all the details there in a slightly longer exhibition. So now going back to HLS, going back to FPGA land, because we are still at the FPL keynote. So FPGAs and CGIs, how do we program them today in HLS? Well, we have actually a relatively long paper for transformations of high-level synthesis codes, so HLS codes, for high-performance computing, showing how to program fast, how to take a temporal language, C and C++, or a control-centric language, and lay it out on a spatial device using pragmas. I could talk about this now, but I don't want to talk about it because, first of all, my student Johannes, who has been driving this in detail, is much better in explaining these details. And second, it will take me more than the allotted time for this talk. So there is a video on YouTube with more than 3.5 hours on how to do this exactly. And Johannes is going into great detail with the HLS tools to show how this works. It's one of our most popular videos on our channel. So I recommend looking out for it. But once you've understood it, you will be in pragma hell. Basically means you write your control-centric code and then you add dozens and dozens and dozens of pragmas to tell the compiler how to execute it. And that is not great. So how do we propose to do this in the future, in the 21st century, in a performance portable way? So we want to have a domain scientist in control-centric land and program in high-level DSLs like TensorFlow, PyTorch, MATLAB, NumPy, and Python in general. Then we have an applied scientist who translates those high-level DSLs, high-level codes, into parametric data flow graphs, our internal representation that is a data-centric internal representation, where then the performance engineer works on that representation with explicit data flow views to build parametric data flow graphs and or optimize parametric data flow graphs, not necessarily build them. And then the framework itself will generate automatically CPU, GPU, and FPGA code in a very specialized form to those specific devices. So at the end, the domain scientist works with a dozen line of codes, which you can very often see in PyTorch. It's a very elegant language. You can write very complex deep neural networks like the GPT network in less than 100 lines of code if you look at MinGPT, so quite elegant. Then the performance engineer is going to write an order of magnitude more lines of code to do the optimization because that's a more advanced task. However, it is still manageable because at the end, the optimized code is going to be thousands, if not tens of thousands of auto-generated code that I don't want to look at. I mean, I'm in the camp of the performance engineers. I like to look at complex code, but not too complex codes, especially not if most of this is at a super low level that is simply irrelevant for the message of the code. And especially domain scientists don't like to look at these great details. At the end, nobody likes to look at vast amounts of assembly code, and the auto-generated code is very close to very low-level assembly code. So now for this, we chose Python as a front end for the program. Why did we do so? Just in August 2022, so very close to the date of the keynote, Python became the top language in the TIOBE index. So it was the first time Python is going through the roof, is their caption. We also support C, but it's not part of this talk. I really want to go more into Python. So Python is the language of choice for computational and data sciences, especially large-scale data sciences. And scientific Python actually has a long history of optimization. So Python has been important in the past, and there are many frameworks optimizing, especially NumPy. So what we do is we want to first understand how well do these frameworks perform before we propose a new framework. So I would like to introduce you to NumPy Bench, or short NP Bench. It's a little benchmark suite that we put together to benchmark or compare various different frameworks in Python. So we took 51 kernels from 9 different domains that are all of manageable size. So they're of the size of these polybench kernels. Actually, all of polybench is part of NumPy Bench, of course, rewritten in NumPy, that we can then execute in a Python environment. We look at 2 different metrics. One is performance, the obvious metric, how fast does it execute. The second one is productivity. How many lines of code do you have to change from a standard NumPy code to the specific framework? Because there is no zero friction environment. At least you need to tell NumPy, use framework X, so that's one line of code change. But many require more lines of code change. So we also have this as an explicit metric. And then we compare different frameworks like the NumPy baseline, which is just NumPy. Then there's Python, Numba, CuPy, NVIDIA's version of NumPy essentially. And then there is DaCe, our framework. So you can easily add more frameworks to this NumPy bench. Then there are, of course, 51 results for all of these different frameworks that I don't want to go through, but you can easily summarize them for the different domains, for the 9 domains. But we can also just look at the totals where we show the speed up relative to the NumPy baseline as a geometric average over the codes that actually compiled in each of these frameworks. And I want to focus us on DaCe GPU and DaCe CPU, which is fundamentally or significantly faster than all the other frameworks, including CuPy on the GPU and Numba or Python on the CPU. So how does this work in detail? And can we make this work for FPGAs, for the FPL audience? And the answer is yes, we can. And then how do we make it work? So here I want to quickly motivate how DaCe works. So it's all about the IR. It's all about parametric data flow graphs, all about the data-centric internal representation. So we take an equation, we take a piece of code, we bracket it into its inputs and outputs. Here we see input is X, output is Y, all the other things are constants in here. We actually forget about the code, we store it in the so-called tasklet, but we don't really look at it in the optimization process because, as I mentioned, it's an order of magnitude cheaper to compute than to move X and Y in and out of the operator. So we call those movements memlets. And of course, now these memlets are almost always array accesses. And if you access an array, there are always many indices of an array, in this case, n indices. And what we do is we could now represent it like this, but we just draw it slightly differently in this, what we call a burger, so top bracket and bottom bracket, and the tasklets in the middle. There can be more complex things in this in this view. And so we have this iteration space representation essentially here. So the tasklet goes through iterations from 0 to n, the iteration space. Now we can have multiple different what we call states, which contain these tasklets. So each of these states is a pure data flow region. So we have a state transitions, which is essentially control flow. So everything within the blue things is just data flow. Everything between the blue things, which are states, is control flow. Okay, so then we have many different concepts like containers, computation, movement, and parallelism in states. So this is quite important to understand. However, here I don't have enough time to go into details. We have a wonderful set of tutorials online on the DaCe webpage where you can learn all of these details. So how do we now go to hardware descriptions? So we take a parallel data flow graph. We just assume that it was compiled to this internal representation, where now I look at the pure data flow sections where all data movement is explicit. You can see these arrows going back and forth, and everything is visible. So it's a perfect environment for spatial mapping. And now we have this automatic code generator that generates some code for the representation. The goal of the performance engineer is now to apply graph transformations to transform that graph into a better representation for a target device like a spatial device like an FPGA. So that's what the performance engineer does. So here with an example, how do we do this in practice? So let's say we look at this very simple combination of XP and the dot product, 2 inputs to XP, XY, and another input to the dot product, then the dot product with the result of the XP called Z, and to the final result. So if we just transform this into an FPGA region, the first thing we do is we need to copy the data X, Y, and W to the FPGA. Well, this is input data on the CPU, needs to go on the FPGA. We perform this in a state that is called pre-XP dot. Then in the next state in XP dot, we actually perform the whole data flow computation. Once that is finished, we copy the data back to the result array on the CPU. Okay, so now the internal memories are replaced with FPGA memories. Of course, they need to be on board. They need to be mapped to either DRAM on the FPGA, or in this particular case, we are mapping it to SRAMs or block RAMs, or depending on what they're called on your favorite FPGA. Okay, so, and then at the end, the data is copied back. This is automatically generated, so none of the boilerplate code has to be written by the implementer. So this is a trivial transformation, of course. The next transformation is not so trivial, because now what we want to do is we want to make sure that we read the elements, the input array, the input elements from the FPGA memory as a stream, so element by element, to move through the circuit in the FPGA. So here we have a visualization of the streaming operator, so they're again represented as maps, and these color-coded output arrays are essentially identifiers of streams that moving in here and then goes into the pink one at the top. and shows the whole streaming architecture, essentially. Again, the code is automatically generated to be a fully streaming code. So then the streaming between the operators, so not streaming from memory into the FPGA, but streaming between the operators for the temporary arrays. This is essentially the same principle. So we are just connecting these stream nodes and automatically generate that code to have a little buffer between these two units that generate the XP output and then consume the dot product input, the left dot product input. Okay, so this is really what these transformations do. At the end, the code is generated for CPUs, GPUs, and FPGAs, but here we are focusing on FPGAs. And this whole streaming transformation is working on Xilinx Vivado HLS codes and Intel OpenCL. So these two these two device types, they differ significantly in the pragmas they require. So you can see here already quite different pragmas. They also differ significantly in their support for different streaming concepts, but at the end, we automatically generate the right code for the right device. So this is what we mean by performance portability. Okay, so this whole boilerplate code that at the end we have here, if you've written an OpenCL program before, you know that in order to write a hello world OpenCL program, you need at least 50 lines of code in C. This is all automatically generated from a single line of Python. So don't worry about this boilerplate. Furthermore, the whole host device interaction with this copy from host, copy to device and whatnot, this will also automatically be generated for the OpenCL, so forget about that as well. And then at the end, what you're doing, all you're interacting with is really a Python API. Furthermore, these programs are really just Python functions that are automatically compiled to the respective C, and in the interface is NumPy arrays, so you can read and write from any NumPy array. So this is relatively productive and relatively simple. And with that, we compile and run a 30 out of 30 Polybench application directly from NumPy on both Xilinx and Intel FPGAs today. So how does this work in practice? What the performance engineer sees. So here you can see how to apply a transformation. So you work on these on these SDFGs, and you can, for example, apply a splitting transformation of these two maps and see what's going on these. You can just see what's happening to the graph when you apply this transformation, and you don't need to worry about bugs in the like off by one bugs when you do the typical tiling. So here in this case, we just tiled the second loop to make it more data movement friendly, and of course we can also undo these operations. So it's really an editor for these programs where you can apply these various transformations. So furthermore, you can actually look at in a specific layover, you can look at the data flow volume between each of those operators, as well as the flops performed by each tasklet. You just hover over it and it'll tell you how many flops are happening in this tasklet, how many flops are happening in this iteration space, and how much data, if you hover over an edge, how much data is moved along every specific edge. So this helps you to understand what your program is doing and to optimize your program further. Then you can also use a debugger. When you want to investigate what's happening in the code, you can also relate it to the C code, the generated one that you can see here. So this is just a little overview of the tool chain that I don't want to spend too much time, and you can find this all in the DaCe SDFG viewer available on the internet, essentially as plug-in for Visual Studio Code. So now I want to talk a little bit about a case study on the weather simulation that we did with Meteo Swiss. Here, this is today running on GPUs. So actually, one of my former students was porting that fully in collaboration with Meteo Swiss, their whole weather code to a GPU-powered system. We were the first worldwide to do this. And the question is, can we do this also on FPGAs? Can we run these weather codes on FPGAs? So we looked at some stencils. We don't have the full code running, but we are relatively close. We could actually get this full code running. But we will see it's not most efficient with today's FPGA architectures. So how do we do this? Well, weather codes are relatively complex stencil programs. They're essentially large dependency chains along those programs. And the idea is just we take these dependency chains and map them to the spatial computing device in our FPGA with a tool that we call StencilFlow. So you can see again at the bottom, you see various references where you can read more about this if you want. So essentially we map these and the stencil programs to a fully pipeline parallel streaming hardware architecture. And we do this transparently to the domain scientist, like I showed before. But let me first summarize a little bit what a stencil operation is. Most of you probably know it. It's a multi-dimensional loop. So in this case, 2 loop over I and j, and then we update each element in this array represented by I and j, in this m by n array in this particular case, and we update it with the north and south neighbor and with the east and west neighbor in these 2 lines of code. So we really, for every element, we read north, south, east, west, and update the point, and then we move to the next element. So relatively simple. Now, a stencil program is a set of stencils combined into a larger graph. So here, both A and B are stencils, and C is another stencil that consumes the output generated by A and B. So we now have 2-dimensional arrays going into A, 2-dimensional arrays going into B that produce each 2-dimensional arrays that are then consumed by C. So it's a more complex, higher level concept. Now, to connect all of these stencil DACs, we have a whole stencil flow stack that we call, we have stencil flow that generates these DACs of stencil programs, and these are then fed through our pipeline to generate code at the end. So let me first describe a little bit how to define those stencils. There is a JSON-based domain-specific language that is now, or that can be automatically generated from a stencil-based DSL like GT4Py. This generates a stencil DAC, and again here these round objects are input arrays. These squares are stencil computations that consume arrays and again output arrays. In the weather and climate lingo, these are often called fields, but in the implementation these are arrays. So this is compatible with the grid tools framework that is developed at CSCS, so you can actually go seamless between those different representations. So now, once you have generated this, you can map this to an abstract hardware to just minimize data movement. Right? So this is the first step. So first we introduce internal buffers to maximize data reuse, and then we need delay buffers to maximize data reuse across operators. So the internal buffers are within a stencil, and then we have to go across stencils because we map multiple stencils to run at the same time on the same device. So the idea is that every input field is read exactly once, and every output field is written exactly once, and everything else happens on chip. So we don't have an I/O problem. We are essentially I/O optimal. That's the goal. We not always achieve this, but that's the overall goal. So the internal buffers, just to show you how this works, remember the stencil is actually reading from north, east, south, and west, and it's going through this array in this form that I'm showing here through this animation. And the buffer area is shown in light gray here, and this is exactly 2 lines, essentially, well, 2 lines plus 1 element that we need to store on chip for this 2D array, and then we just stream this in and we retire the data on top. Right? So we essentially have to have enough buffer space to store these 2 lines, and then we read every element only once. So this is great. In 2-dimensional stencils, we buffer 2 rows. In 3-dimensional stencils, we need to buffer 2 2D slices. So in general, in k-dimensional stencils, we need to buffer k-1 dimensional large sub polyhedra. Okay, and so if we can do this, if you have enough chip space, then we can make sure that every stencil operation reads the input only once. Right? For 2D, that's simple. Fortunately, for weather and climate codes are almost always working on 2D stencils. The 3rd dimension, the height dimension, the atmospheric dimension is handled separately with a different solver, so we don't necessarily have so many operations there or so many stencils there. So in the global reuse case, this is now the stencil program among multiple different stencils, in this case A, B, and C. There could be different cases where, for example, the input is used by multiple different stencils that have a dependency between them. So this array D is consumed by both A and C, or a result that is produced here, in this case by A, may be consumed by 2 different stencils, in this case B and C. The principle is the same, so we need to make sure that the streaming just aligns, even though C will need the stencil or each input of this array later than B, because C can only run once B has produced the element. So this is quite important and a concept that is very familiar for many of you in this FPGA area. So-called delay buffers are used to solve this. But let me just show this differently here. We again have the stencils A, B, and C, the output of stencil A is consumed by both B and C, or written to both B and C. So, and then we of course have buffers at each of the inputs, and we have some flow control algorithm that makes sure that these buffers are not overwritten at the wrong time. So B has 2 input buffers, C has 2 input buffers. So what's now happening, we stream the first element out of A, it's A0, it goes to both C and B as the consumers, and then we stream the second element A1, but unfortunately C cannot be active, cannot consume A0, which means that the channel is stalled, so the channel is still full and A1 cannot progress. And then we, of course, push back into this B to A channel, and well, mainly because the C to A channel is full, and we now have a deadlock situation because the path is just full. The way to solve this is relatively simple. We introduce a delay buffer that just buffers that additional A1 element such that B can now get active. So now B is able to produce B0, and then C is able to consume A0 and B0, and then we can move to the next element, and we can just cycle this through. So very, very similar principle to what is often used in hardware design at the low level. Okay, so the path delay is then, of course, important to determine the internal buffer size and the pipeline depth. So this is how it works. Now I want to talk about some performance results on a Stratix 10 on a bitware board that was provided to us, fortunately, by the University of Paderborn. I want to thank them again here for their gracious support or access to their systems. So if you look at the amount of resources we give on the x-axis, so ranging from 512 to 3072 units, and the performance we achieve, you can see that in the single node case, we can go up to 3072 FP32 units that we can synthesize in hardware on the FPGA, which gives us about 568 gigaops per second for this particular FPGA. If we go multi-node now for 2 FPGAs, we can double that. For 4 FPGAs, we can double that again, and for 8 FPGAs, we can double that again. So you can see the performance goes up to quite impressive ranges. The communication in this case is implemented by the streaming message interface, which is an MPI style streaming interface for FPGA, distributed FPGA communication that was proposed at Supercomputing 2019, and you can also use and download that code developed by one of my postdocs, Tiziano De Matteis. Okay, so now if you look at these very simple stencils and compare it to existing stencil codes that people have hand optimized, like this case, the Diffusion 2D and Diffusion 3D, optimized by a very competent researcher, Zuhuri, in a paper a while ago, we actually achieve with our stencil optimized, spatial programming optimized implementation slightly higher performance than the manually optimized OpenCL code. So that is quite nice. And it runs from Python. So it's actually much simpler than dealing with the OpenCL code. So now this was an example for single stencil optimization, simple iterative stencils. But now let's move to these complex stencil programs, and we just look at one particular example in the StencilFlow DSL. And again, this can be derived from grid tools developed at CSCS. This stencil here, quite complicated. I don't want to talk too much about it. It's a complex stencil DAG. It is actually one of the more complex stencils in this weather code, but there are many dozens of those. So this is just one little piece. It has about 130 floating point operations, 20 data-dependent branches, and a relatively bad arithmetic intensity. However, since we can just stream through this stencil, the arithmetic intensity is not too bad at the end. So implementing this on a Stratix 10 device, we get about 145 gigaops, and we realize that we are essentially memory bound. We are achieving 50% of the peak memory bandwidth of 77 gigabyte per second, which is the 145 gigaops, significantly more than a 12-core Xeon that has about the same memory bandwidth, but a much lower efficiency for accessing this memory. However, if we now compare this to a P100 or V100 NVIDIA GPU, we see that the performance is significantly lower, but we can also see that they're somewhat cheating because their peak memory bandwidth is a factor of 10 or more higher. And so they achieve a much lower utilization of their memory. So now the question is, how far can we go if the Stratix 10 had faster memory? That's relatively easy with FPGAs. We just feed random data instead of reading it from memory through the computational circuit, and we get 513 gigaops per second, which is more than twice as fast as the P100 and nearly competitive with the V100 in that particular case. So it's actually not too bad. If we had HBM on the Stratix 10, which we don't, but more modern FPGAs have HBM. So we actually get respectable frequency and respectable DSP utilization. So we realize FPGAs today, or maybe tomorrow, have insufficient bandwidth, but that is fixed with these HBM FPGAs. But they're super nice in exploiting deterministic bandwidth and use pipeline parallelism very efficiently. And our framework, DaCe framework, can just generate this. So you can reproduce this, you can download StencilFlow from our GitHub repository. We would love if you play with it, and we would be happy to answer your questions. So now, can we get to full weather and climate codes on FPGAs today? The answer in the context of the digital twin project that we defined in this Nature paper about a year ago is unfortunately no, because GPUs are still the more encouraging option, but this is due to technical details. I personally believe that devices like the upcoming Xilinx ACAP device could have the opportunity to beat GPUs due to that on-chip streaming capability that leads to, in the spatial programming context, to much higher data efficiency than this TikTok design that also GPUs have. So again, back to the control locality that I defined earlier in this talk. I think control locality is going to be key to achieve data efficiency and energy efficiency in future compute devices. Another observation in this mapping to spatial devices is actually frequency. So many of the designs that we play with get us very suboptimal performance, often smaller than 200 megahertz. And if you talk to or at least if you read the specs for the Xilinx and, AMD and Intel FPGAs, they should have much higher frequency than 200 megahertz. Actually, they're ranking at 650 and 800 megahertz respectively. So why do we achieve less than 1/3 of their key frequency? Well, if you actually look at the designs, and here's a picture of one of those designs after place and route, and in red we have a critical path. We can see the critical path is here through the whole chip, going from the bottom to the other side of the chip. So why is it going through half of the full chip? Well, it's pretty clear, because pretty much everything is connected to memory. The HLS tool does a pretty bad job placing these things at the global level. So what do we propose now? Well, we propose to cut out small pieces, because in our data flow graph, we already have these small pieces like this yellow thing here, another yellow thing, and another yellow thing, and treat these small pieces as separate blocks in placement and route. And then the surrounding I/O shell that is then doing the memory access, we place manually. And what we can then actually do is since these pieces are so small, we can double pump them. We can run those at a much higher frequency than the surrounding pieces and the infrastructure pieces. And this is often called double pumping. It's exactly a principle that is used by AMD today, that was just announced last week, in the implementation of the AVX 512 unit. It's essentially a 256-bit unit that runs twice as fast as the surrounding logic with a principle called double pumping. So we can do the same thing. But we do it automatically, not manually designed like AMD does in RTL, but we do it on our internal representation like a compiler optimization for emitting these spatial programs. We know vectorization today. There are two different principles of vectorization. So where we can have vector addition, for example, or reduction vectorization. I don't want to talk about these because those we both understand. But now the principle of temporal vectorization is essentially we can take arbitrary functions with arbitrary dependencies and simply clock on an FPGA those regions that are that contain this code faster than the surrounding regions, and we can now feed more of those into those regions, of course. So this is a form of vectorization, but it's not on the spatial domain, it's on the temporal domain, because these regions just run twice as fast or 4 times as fast. And this is quite a cool principle, and we can do it fully automatically in our DaCe framework. So we take one of those SDFGs, we look at the vector addition, and then we simply introduce the streaming principle. We compile this to streaming like I discussed before, but then we take the multi-pumped region as a separate region, introduce synchronization and issue buffering functionality, and then just run this inner kernel, the vector addition, twice as fast as the surrounding kernel, and generate separate code, different codelets that we then compile or put together through an IP linker in the Xilinx tool chain to have different IP blocks running at different speeds. By the way, OpenCL, you cannot do this today. In OpenCL, it does not allow you to have different speeds, so we had to tinker with explicit RTL or IP block integration in the tool. This paper is going to appear at ICCAD, and Carl Johnson has done a great job of putting this all together, a collaborator from Denmark. So now, if you look at the performance of temporal vectorization on this Alveo U280, so we compare this to a manual code communication avoiding implementation, with the O is essentially the HLS implementation, and the DP is short for double pumped, so this is the higher frequency version. So here in the first two versions, the CA and the O version, we have only one clock domain, and in the last version we have the second clock domain, which is our inner kernel, that runs nearly twice as fast, and then of course gives us a much higher efficiency for the DSPs, because they are now also running about nearly twice as fast. We can also do this for a Jacobi stencil. The first one was matrix multiplication. We can do this for a 3D stencil, very similar results. We can do this for another 3D stencil, so essentially the diffusion stencil I talked about earlier, with very similar results here again. Okay, so with that, I want to come close to a conclusion. We have the DaCe framework that can take various inputs. I only talked about NumPy, but we also have DaceML, C grid tools that I also mentioned, and in planning Fortran frontend. We have many output or code generators. I talked about the Xilinx and the Intel FPGA outputs. We also have ARM, SVE, and various CPU and GPL codes. And it's relatively easy to extend to your favorite output or input language. So we encourage you to do so. Very soon we will actually have support for deep learning codes through the Onyx exporter of PyTorch or TensorFlow. And we have an importer from Onyx into our internal representation, and of course all the code gens. Early performance results, as you can find in this paper down here at ICS, are extremely promising, and this is also base of the paper that I mentioned earlier. So this framework is ready for prime time. We have used it in our Gordon Bell Prize 2019 as a base for the code, so we still had to write a lot of manual code there, but we believe now that it's much further along to fully support a tool flow that would support real programs, and we are working on many of those. And it would be great if you would join us. If you're a PhD student, or if you're looking for a PhD position or a postdoc, please apply through our webpage. We have many open positions in the DaCe context, but also many other contexts in my lab at ETH Zurich. So with that, I would like to summarize quickly. So high performance computing is a data management challenge. We have various ways of solving this, which I discussed in DaCe. We look at NP-bench as a benchmark. We generate various hardware descriptions. We have a prototype stencil flow implementation where we can map climate stencils or climate stencil programs to FPGA devices. We have encouraging first results. And I would like to also point you to our YouTube channel where this video is hosted, which you can see down here, the URL, or simply Google for Scalable Parallel Computing Lab at ETH Zurich on YouTube. And you find many more of those videos, either me speaking or members of my lab speaking, if you enjoyed that presentation, about many of the details of pretty much all our papers. Thank you very much, and then goodbye.